Fish and shellfish concentrate mercury in their bodies, often in the form of methylmercury, a highly toxic organic compound of mercury. Fish products have been shown to contain varying amounts of heavy metals, particularly mercury and fat-soluble pollutants from water pollution. Species of fish that are long-lived and high on the food chain, such as marlin, tuna, shark, swordfish, king mackerel, tilefish, and northern pike, contain higher concentrations of mercury than others. Mercury is known to bioaccumulate in humans, so bioaccumulation in seafood carries over into human populations, where it can result in mercury poisoning. Mercury is dangerous to both natural ecosystems and humans because it is a metal known to be highly toxic, especially due to its ability to damage the central nervous system. In human-controlled ecosystems of fish, usually done for market production of wanted seafood species, mercury clearly rises through the food chain via fish consuming small plankton, as well as through non-food sources such as underwater sediment. This mercury grows in concentration within the bodies of fish and can be measured in the tissues of selected species. The presence of mercury in fish can be a particular health concern for women who are or may become pregnant, nursing mothers, and young children. Biomagnification. The consumption of fish is by far the most significant source of ingestion-related mercury exposure in humans and animals. Mercury and methylmercury are present in only very small concentrations in seawater. However, they are absorbed, usually as methylmercury, by algae at the start of the food chain. This algae is then eaten by fish and other organisms higher in the food chain. Fish efficiently absorb methylmercury, but only very slowly excrete it. Methylmercury is not soluble and therefore is not apt to be excreted. Instead, it accumulates, primarily in the viscera, although also in the muscle tissue. This results in the bioaccumulation of mercury, in a buildup in the adipose tissue of successive trophic levels, zooplankton, small nekton, larger fish, and so on. The older that such fish become, the more mercury they may have absorbed. Anything that eats these fish within the food chain also consumes the higher level of mercury that the fish have accumulated. This process explains why predatory fish such as swordfish and sharks or birds like osprey and eagles have higher concentrations of mercury in their tissue than could be accounted for by direct exposure alone. Species on the food chain can amass body concentrations of mercury up to 10 times higher than the species they consume. This process is called biomagnification. For example, herring contains mercury levels at about 0.1 parts per million, while shark contains mercury levels greater than 1 part per million. Legislation. Japan. Since the Manometer disaster, Japan has improved on its mercury regulation. During the 1970s, Japan made strides to reduce mercury demand and production. Chief among these efforts was the reduction of inorganic mercury produced by mines. It was halted by 1974, and demand fell from 2,500 tons per year in 1964, its peak, to 10 tons per year in recent years. Since these initial strides, Japan has introduced a list of regulations governing the mercury content of a variety of materials. Regulation of these potential sources of pollution reduces the amount of mercury that ends up in fish and, through biomagnification, in humans. In addition to enacting legislation controlling the mercury levels in potential pollutants, Japan has directly influenced the environment by issuing regulations setting acceptable levels of environmental mercury pollution. It is Japan's goal to promote international mercury legislation in hopes of preventing any country from experiencing what it did. Despite Japan's extensive regulation and experience with mercury-based disasters, there is still little information provided to the public. The Japanese Federal Fish Advisory's recommendations are less strict than those in America. United States of America. The United States is a leader in mercury regulation. A key piece of mercury legislation in the United States is the Mercury and Air Toxics Standards. This policy was finalized by the Environmental Protection Agency on December 16, 2011. This is a federal policy which directly influences mercury in fish, and is the first of its kind in the United States. The facilities targeted by this new policy are the chief sources of mercury in the air. The airborne mercury is dissolved in the oceans, where microorganisms convert waterborne mercury into methylmercury. Mercury thus finds its way into the food chain and into fish. MATS is legislated towards the aim of preventing about 90% of the emissions from power plants from reaching the air. In total, the expected health benefits are estimated at $37 billion, $90 billion by 2016. In comparison, the expected economic cost is $9.6 billion annually. Another integral piece of legislation controlling the emission of mercury to the air is the Clean Air Act. Under this act, mercury is classified as a hazardous air pollutant, allowing the EPA to regulate emissions by establishing performance standards. International legislation on a global scale is believed by some to be needed for this issue because mercury pollution is estimated to be so far-reaching. Pollution from one country does not stay localized to that country. Despite the need by some, international regulation has been slow to take off. The first forms of international legislation appeared in the 1970s, beginning as agreements about shared bodies of water. The next step was the Stockholm Declaration, which urged countries to avoid polluting the oceans by dumping. The 1972 Oslo Convention and the 1974 Paris Convention were adopted by parts of Europe. Both lessen polluting the ocean with mercury, the former by banning the dumping of ships and aircraft into the ocean, and the latter by obligating participants to reduce land-based pollution on coastlines. The first real global legislation regarding mercury pollution was the Basel Convention of 1989. This convention attempts to reduce the movement of mercury across borders and primarily regulates the import and export of toxic chemicals, including mercury. In 1998, the Convention on Long-Range Transboundary Air Pollution was adopted by most of the European Union, the United States, and Canada. Its primary objective is to cut emissions of heavy metals. The convention is the largest international agreement on mercury established to date. In the early 21st century, the focus of mercury regulation has been on voluntary programs. The next phase in legislation is a global effort, and this appears to be what the Manometer Convention hopes to accomplish. The Manometer Convention, named after the Japanese city that suffered horribly from mercury pollution, has taken 4 years of negotiation but was finally adopted by delegates from over 140 countries. The convention will come into power after 50 countries have signed it. The Manometer Convention will require all participants to eliminate, where possible, the release of mercury from small-scale gold mining. It will also require a sharp reduction in emission from coal burning. Levels of contamination. Most contaminated fish species. The danger level from consuming fish depends on species and size. Size is the best predictor of increased levels of accumulated mercury. Sharks, such as the mako shark, have very high levels of mercury. A study on New Jersey coastal fish indicated that 1/3 of the sampled fish had levels of mercury above 0.5 parts per million, a level that could pose a human health concern for consumers who regularly eat this fish. Another study of marketplace fish caught in waters surrounding southern Italy showed that, undoubtedly, greater fish weight leads to additional mercury found in fish body tissues. Moreover, the concentration, measured in milligrams of mercury per kilogram of fish, steadily increases with the size of the fish. Anglerfish off the coast of Italy were found with concentrations as high as 2.2 mg of mercury per kilogram, higher than the recommended limit of 1 mg of mercury per kilogram. Annually, Italy catches approximately a third of its fish from the Adriatic Sea, where these anglerfish were found. Fish that consume their prey in a certain manner may contain much higher concentrations of mercury than other species. Grass carp off the coast of China hold far less internal mercury than do bighead carp. The reason for this is that bighead carp are filter feeders, while grass carp are not. Thus, bighead carp gather more mercury by eating large amounts of small plankton, as well as sucking up sediments that collect a sizable amount of methylmercury. U.S. government scientists tested fish in 291 streams around the country for mercury contamination. They found mercury in every fish tested, according to the study by the U.S. Department of the Interior. They found mercury even in fish of isolated rural waterways. 25% of the fish tested had mercury levels above the safety levels determined by the U.S. Environmental Protection Agency for people who eat the fish regularly. Origins of mercury pollution. There are three types of mercury emission: anthropogenic, re-emission, and natural, including volcanoes and geothermal vents. Anthropogenic sources are responsible for 30% of all emissions, while natural sources are responsible for 10%, and re-emission accounts for the other 60%. While re-emission accounts for the largest proportion of emissions, it is likely that the mercury emitted from these sources originally came from anthropogenic sources. Anthropogenic sources include coal burning, cement production, oil refining, artisan and small-scale gold mining, wastes from consumer products, dental amalgam, the chlor-alkali industry, production of vinyl chloride, and the mining, smelting, and production of iron and other metals. The total amount of mercury released by mankind in 2010 was estimated to be 1960 metric tons. The majority of this comes from coal burning and gold mining, accounting for 24% and 37% of total anthropogenic output respectively. Re-emission, the largest emitter, occurs in a variety of ways. It is possible for mercury that has been deposited in soil to be re-emitted into the mercury cycle via floods. A second example of re-emission is a forest fire. Mercury that has been absorbed into plant life is re-released into the atmosphere. While it is difficult to estimate the exact extent of mercury re-emission, it is an important field of study. Knowing how easily and how often previously emitted mercury can be released helps us learn how long it will take for a reduction in anthropogenic sources to be reflected in the environment. Mercury that has been released can find its way into the oceans. A 2008 model estimated the total amount of deposition into the oceans that year to be 3,700 metric tons. It is estimated that rivers carry as much as 2,420 metric tons. Much of the mercury deposited in the oceans is re-emitted. However, as much as 300 metric tons is converted into methylmercury, while only 13% of this finds its way into the food chain. That is still 40 metric tons a year. Much of the mercury that eventually finds its way into fish originates with coal-burning power plants and chlorine production plants. The largest source of mercury contamination in the United States is coal-fueled power plant emissions. Chlorine chemical plants use mercury to extract chlorine from salt, which in many parts of the world is discharged as mercury compounds in wastewater, though this process has been largely replaced by the more economically viable membrane cell process, which does not use mercury. Coal contains mercury as a natural contaminant. When it is fired for electricity generation, the mercury is released as smoke into the atmosphere. Most of this mercury pollution can be eliminated if pollution control devices are installed. Mercury in the United States frequently comes from power plants, which release about 50% of the nation's mercury emissions. In other countries, such as Ghana, gold mining requires mercury compounds, leading to workers receiving significant quantities of mercury while performing their jobs. Such mercury from gold mines is specifically known to contribute to biomagnification in aquatic food chains. The farming of aquatic organisms, known as aquaculture, often involves fish feed that contains mercury. A study by Jardin has found no reliable connection between mercury and fish food affecting aquaculture organisms or aquatic organisms in the wild. Even so, mercury from other sources may still affect organisms grown through aquaculture. In China, farmed fish species, such as bighead carp, mud carp, and mandarin fish, carried 90% of total mercury content in all of the measured fish in a study by Cheng. This study also concluded that mercury bioaccumulates through food chains even in controlled aquaculture environments. Both total mercury and methylmercury absorption was found to be derived from sediments containing mercury, not mainly from fish feed. The Hawaii Institute of Marine Biology has noted that fish feed used in aquaculture often contains heavy metals such as mercury, lead, and arsenic, and has dispatched these concerns to organizations such as the Food and Agriculture Organization of the United Nations. An industry aquaculture company, Aquatic Farms Limited, has posted numerous guidelines on how to keep fish feed safe, thus protecting the consumer from any dangers posed by the food eaten by commercial seafood species. Some guidelines include providing a cool and dry environment to prevent both spoilage and contamination of the fish feed and avoiding pesticides and other chemicals up to a certain limit. Elemental mercury often comes from coal power plants, and oxidized mercury often comes from incinerators. Oil-fired power plants also contribute mercury to the environment. The energy industry, therefore, is a key player in the introduction of mercury into the environment. When addressing the issue of reducing seafood mercury bioaccumulation on a global scale, it is important to pinpoint major energy producers and consumers whose exchange of energy may be the root of the problem. Controlling output of mercury pollution sources. A study that was led by scientists from Harvard University and U.S. Geological Survey has determined that in the next several decades there will be a 50% increase in mercury levels. The study also shows that the increases are connected through industrial emissions and are not natural as previously thought. However, by decreasing emissions from industrial plants, the possibility of decreasing the high level of mercury remains plausible. Air pollution control devices have been implemented in South Korea as the government is starting to take inventory of mercury sources. Mercury pollution can also be removed by electrostatic precipitators. Bag-based filters are also used in factories that may contribute mercury to the environment. Flue gas desulfurization, normally used to eliminate sulfur dioxide, can also be used in conjunction with APCDs to remove additional mercury before exhausts are released into the environment. Even so, countries such as South Korea have only begun to use inventories of mercury sources, calling into question how fast anti-mercury measures will be put into factories.